Hello, and welcome to linear algebra. So we'll talk today about complex matrices and diagonalization. This will be the tough lecture of the series. This is part of a series, 6 lectures, and this is really the tough part. So we've seen real matrices before, a lot of interesting things that we can do with them. But we're missing somehow eigenvalues for all these matrices. This can be complex in general, that's the point. So even for studying the complex, the real matrices, you need complex ones. So the whole theory today. Let's find this presentation. So here we go, complex matrices and diagonalization. So that's the core of the whole linear algebra theory, the most important course. So let's start with complex numbers. So these are, a plus I, bi squared is minus 1. They can be represented in the plane, okay? So z is ab. So you put the real part here, imaginary part here. And you have this formula, also exponential. So given a point in the plane, you can write it in polar coordinates, okay? You have the r, the distance, and t is the angle, right? So r is, of course, well, the distance from 0 to AB by Pythagoras is square root of a squared plus b squared. Now in this triangle here, this side is b, this side is a. So the angle is given by tangent is b over a. Now the formula itself is, of course, extremely complicated. I mean, there's a lot of analysis here. So if you don't know the proof, just use it. And well, actually, very few people, even among professionals, really know what's going on with this formula. It's really hard to prove. Okay, but we'll use it. Now, what's the point with these numbers? Well, it's for having solutions to x squared is minus 1. Whenever you need a solution, that's your solution, I and minus I2 actually. And in fact, even more generally, any polynomial has solutions, has roots over the complex numbers. You see, so x squared plus 1, that's a polynomial. It has no real roots. But when going to complex numbers, it has 2 roots. That's actually true for any polynomial p. So you take a polynomial of degree n, it has n roots. So that's why the complex numbers are important. Whenever you need weird numbers satisfying weird equations that have obviously no solutions, go to complex numbers, you find the solutions there that you can use afterwards. Also importantly, I mean, this was a bit abstract and mathematical, but in real life, somehow, these are very important in physics, especially in quantum physics. Well, it's not exactly real life, but if you look at the microscope, you put a pile of microscopes somehow to see what happens at really very, very tiny scales where you have the electrons and all that. These guys there, the electrons and everything, they don't live in R3, they live in C to the infinity. So they have an infinity of coordinates which are complex. That's the thing. So all these applications of quantum physics, computations, they require complex numbers. But for us, we're mostly interested for the moment in this, in polynomial solutions. That's on account. Now, as a first application, well, let's just take our favorite matrix, the rotation of angle t. So obviously there's no eigenvalues, right? Because it rotates, it cannot be proportional. But as strange as it might seem, it has eigenvectors, complex eigenvectors. You see, if I take RT and multiply by 1i, I get these guys here, so it's a multiple of 1i. Scalar being this complex number, exponential of I minus t. And same for 1 minus i. You get this. The eigenvalue is exponential I minus exponential of it. So this means that RT is diagonalizable over C. That was very bizarre, but it's good. I mean, right? Whenever you have a diagonalization, you can do a lot of things afterwards. Matrix becomes extremely simple. So this is one thing. Now, even more magics. Now you can do something else now. So remember, this rotation happens in the real plane. Now this real plane is just complex numbers, right? So this rotation is actually a linear map from what? From C to itself. So it's a 1 by 1 matrix because you're in 1 complex dimensions. So the formula of this matrix was the rotation of angle t. It's multiplication by exponential it. So it's a 1 by 1 matrix, okay? So this is even perhaps even more powerful. I mean, this rotation can be diagonalized in C. That's very good. It's even better. I mean, it's something completely trivial if you look at this in this way. So this is somehow the scary matrix, the rotation of angle T. It's not at all scary complex. It's just a number. Okay, now let's go now a bit into details in all this. So I have all this theory that we explained in the first two lectures in the real case, like linear maps, eigenvalues, determinant, all that. Basically everything extends to a complex case with a few subtleties. So let's take a look at this. First of all, any linear map is of this form. F of V is AV, multiplication by a matrix. It's clear. Also, in the rectangular case, I mean, it takes spaces of different dimension. The matrix is rectangular. It's exactly as in the real case. Finally, also exactly as in the real case, with this notation, so FA is the multiplication by A, we have FAB is FA of B. So composition of linear maps corresponds to composition of matrices. So in particular, if you want to invert a map, you have to invert the matrix, right? This second formula follows from the first one. Now, what else do we know? The determinants. Now, the determinant, we've seen many definitions for it, and if you want to speak about volume somehow in complex, it's a bit headaching. So let's better not do that, and let's pick this as a definition: the formula over with sum over permutations. The formula, okay? So you take the same formula that takes sum over permutations of, and you take products like this, following the permutation, and with the sign there, the so-called signature of the permutation. Some of these guys, that's your determinant. And all this obviously works in complex too. I mean, you can define it like this, and then you have same properties as in the real case. So it's linear in the columns. These are the formulas. You can multiply or subtract. I mean, this is just linearity, but it's better to say it in this way because in practice, that's how you come to determinants. You always multiply rows and subtract, right? Also, you have that AB is that A that B, and also determinant of the transpose is the determinant. All these things now, they're a bit trickier to prove that. In the real case, this was obvious because it's the volume and you inflate somehow by A and B. In the complex case, well, it's hard to work out the geometry of all this because it's complex, but you can prove this with some combinatorics. You just have the formula plug into some combinatorics and you get it. And same for the transpose. Actually, the transpose, yeah, it's very simple. This one requires it's 10-minute computation, let's say. So everything fine. Yeah, so eigenvalues. Now that's the last thing we learn about real matrices. Same definition, AB is lambda V. That means that V is an eigenvalue, eigenvector, the eigenvalue lambda. And now, well, when does this happen? When A minus lambda times V is 0. So A minus lambda must be not invertible, so the determinant must be 0. So you get this thing on the theorem. Now, eigenvalues are the roots of the characteristic polynomial. Now, as an example, well, let's just take the general 2 by 2 case. Okay, so it's in the rotation already. So you take this matrix ABCD, characteristic polynomial. Don't need to compute it every time. It's very simple. So here's the trick. It's lambda square minus A plus D, and then you put the determinant. So this is eigenvalues. Actually, does not need to compute even the polynomial. So the eigenvalues, that's what you need to always remember. The sum is the so-called trace of the matrix. It's A plus D, and the product is the determinant. So usually for most matrices, well, those integer coefficients, whatever, you can solve this in your head, right? If you can solve it, well, you can use the formula for the degree to polynomial. Okay, so we always have eigenvalues to complex eigenvalues for matrices, real or complex. Very good. Now, in principle, with this we can diagonalize now in complex. So here is the theorem, and it's quite subtle. Okay, so let's go slowly. So you take a matrix, can be real or complex. Let's take it complex, that's the most general. Consider a characteristic polynomial, decompose it into factors. So first you have a sign here because you see this minus x will come on a diagonal If you make the product of minus x's, that's the highest term, it's going to be minus x to the n. So that's why the sign is minus 1 to the n. And then you have some x minus lambda I, some roots, right? This might be distinct or not. I mean, let's just write it like this. Now, let's pick a number here and consider the corresponding eigenspace. So that's the vectors v with the v is lambda v. Then the theorem says several things. So first is that these eigenspaces are always don't reduce to 0. They have at least dimension 1. And that's the bound from below. And the bound from above is that, you see, each lambda comes with a multiplicity here. You can look how many times it appears between the roots. And the dimension is more equal than the multiplicity. And that's the main part of the theorem, which comes now. The matrix is diagonalizable precisely when we have equalities everywhere here. So the dimension of the eigenspaces should be equal to the multiplicities. So that's the big theorem in linear algebra. Now, in practice, if you want to apply this, well, it's here is the application. It's a kind of algorithm, so you have to go slowly. It takes, I don't know, 3 by 3 matrices. When you're a beginner, it might take half an hour. You should get to 10 minutes. I think that's very reasonable. Yeah, think. But you have to do it every time. You have to think a bit. So first of all, of course, computer characteristic polynomial, factorize it. There are some tricks for this. We'll be back to this later. That's definitely in the first part, right? Let's go back to the slide here. Yeah, compute factorize. And then we have to compute these eigenspaces and make a discussion here if we have equalities or not. That's a bit more complicated. So what's the plan? So one, you do this definitely. Now once you're done with one, you stop a bit because the question is the matrix diagonalizable, right? If it's not, you're done. So if the eigenvalues are distinct, A is certainly diagonalizable because let's go back here, you see, the dimensions are greater than 1. Now if the eigenvalues are distinct, there are n things here, so it's between 1 and 1. It's equality, right? This happens. So if lambda are distinct, this means that, yeah, you definitely have to work. It won't be done before time. Also, another important remark is that if some eigenvalue, even if your matrix is real, if some eigenvalue is not real, it is not diagonalizable over R. So if you're ever looking for a diagonalization over R, you find a complex eigenvalue, game over. There's no diagonalization. Okay, so once you're done with this, well, you have to solve these equations now, compute eigenspaces, and you look at dimensions. If they don't work, it's not diagonalizable, game over. In case it works, well, you have to find the basis of each of these spaces, and you put together all these bases as full vectors in a matrix that you call P, the passage matrix. Also, you put all the eigenvalues that you found on the diagonal of matrix D. You have to compute the inverse of the passage matrix, and then that's your final formula. A is PDP minus 1. Okay, so D is the diagonal, P is the passage matrix. So there's all this work to be done here. Now some tips for into dimensions regarding the first part, polynomial and factorization. Well, you don't need polynomial all that. I mean, just the sum is the trace, the product is the determinant. This is actually true in general. It's good to know this. Sum of the eigenvalues is the trace. The sum of on the diagonal, the product is the determinant. Now, in order to factorize now a polynomial in n degree n, well, there's no really algorithm. So, but if the polynomial has integer coefficients, look first for an integer roots, and this, if you do some number theory, is very simple. This must divide the last term, I mean the one without x, the coefficient of x0. So that's the thing. I mean, if you have polynomial integer coefficients, look at the divisors of this this last term and try them. Maybe there's a root among them. That's usually what must be done. Now, regarding the second part, when computing eigenspace is important, always start with eigenvalues having big multiplicity. Why? Because if you start with an eigenvalue of multiplicity 1, well, definitely you'll get a space of dimension 1, right? Let's go back to the theorem. So if I put 1 here, the dimension is 1. So you're done with that, and you have to compare it for another eigenvalue. But if you start with an eigenvalue with big multiplicity 2 or more, it might happen that the dimension is not the good one. So then A is not diagonalizable and game over. Okay, so never start with the simple eigenvalues because this is something constructive somehow, and after all, A might be not diagonalizable. Also, of course, double check computations. Many problems actually involve a parameter, so yeah, just plug in T0 from time to time to double check. Yeah, computation. I mean, there are many computations. Let's go back to the algorithm here. If you fail one of them, the final answer will be wrong. It's more 0. But double check all the time, and that's particularly useful when you have a parameter. Just plug in T0. Usually it takes a few seconds to verify. So good luck with all this. You'll have to work. Usually when you're a beginner, it takes 30, maybe 45 minutes, and then after 10 matrices, I'm talking about C/C matrices. These are important. Maybe after 10 matrices, you get to 20 minutes, and if you're more advanced, you should get to 10 minutes. That's the end of the game. Now let's just go more advanced theory now. So what we can do in complex and we can do in real, well, unitary transformations, things like that. So let's talk a bit about this. So I'll put the scalar product, the usual one on Cn, and I'll define the algebraic matrix like this. A star ij is the transpose, but the bar. So what's the point with all this is that with respect to the scalar product, you have this formula which is extremely useful. X scalar y is x a star y. Proof is just trivial. Now with this, for instance, you can prove the following thing. So for a matrix, the corresponding transformation x goes to ux preserves the scalar product, some of the geometry of Cn, if and only if u star is u minus 1. That's a so-called unitary matrix. Why is this true? Because use this formula here, you see, ux scalar uy is x u star y. So if this should be equal to xy for any xy, this must be the identity. So u star is u minus 1. So that's a unitary, very important matrices. Now, here are some theorems now about diagonalization. So if the matrices are normal, meaning that they commute to the adjoint being this beast here, transposed with the bar, then they are diagonalizable. That's a deep theorem. We'll be back to it later, a bit of proof in further lectures. Now, the matrices which are self-adjoint, in particular, if it's equal to a star, of course, they are diagonalizable as a consequence of this. And moreover, the eigenvalues are real. So these are some of the analogs of the real matrices. It's a bit subtle here. And finally, the matrices which are unitary, in the sense that we said before, u star is minus 1, are also diagonalizable because, right, you commute to the star. These products are 1, and the eigenvalues are the unit circle. So I've seen an example actually of this. The rotation of angle t is unitary. The eigenvalues, if you remember, were exponential it and minus it. So these are the unit circle. Okay, so these are quite deep theorems. We'll be back to them in next lecture of proofs. But that's very important. Yeah, so spectral theorem. Now, more advanced stuff, this is always good to know. So the matrices having distinct eigenvalues are dense. In particular, the diagonalizable matrices are dense. That's a bit tricky using the resultant of polynomials. And I mean, R is 0 is this. That's a hypersurface. And dense complements. Well, this is very interesting because any formula which is true for diagonalizable matrices must be true in general somehow. So this is very good to know. And finally, one more thing, well, in case there's no diagonalization, you have to use the Jordan form. That's it. So you can put matrix with Jordan blocks like this. Each block has the eigenvalues followed by 1s. So in case, of course, the matrix is diagonalizable or the Jordan blocks are 1, 1 blocks, and you get the results. Okay, guys, so we've seen a lot of things. So we'll be back to things which are missing somehow the next times. So hope you like it. See you soon.